Hello, this is Walter Leite, and in this video, I will demonstrate how to estimate the treatment effect with differences in differences and with fixed effects and random effects models in R and RStudio. So the example is using data from the early childhood longitudinal study, 1996 kindergarten cohort, and the objective here is to estimate the effect of mobility on reading achievement between kindergarten and fifth grade. Now, mobility means the students change schools from one year to the other. So change school is coded as one for the year immediately after the student changed and zero otherwise. It's a repeatable treatment, so individuals can move more than once. Now, the ECLSK has sampling weights and strat IDs and cluster IDs, which describe the complex survey methods that they use, but we are not going to use it in this example. So we start loading the data. It's a subset of the ECLSK where individuals that moved at least once between kindergarten and fifth grade. Now, differences in differences is used for a design that's pre-test and post-test. Therefore, for demonstrating difference in differences, I took a subset where I just take kindergarten and first grade. Okay, to answer the question, does change in school between kindergarten and first grade have an effect on reading scores? Right, so I only take two measurements, the pre-test is kindergarten, spring of kindergarten, post-test is spring of first grade, and the treated group are those that moved, that changed schools between kindergarten and first grade, and the control group are those that don't, right? So I selected this data set with just two measurement points from the bigger data set. Here, so here is subset with just time period 1.5 and 2.5, and create this new data set called data DD. And then I create a pre and post variable coded as 0 and 1. And I end up with this data set where I have pre and post, 723 observations in each, and treated them, and control 810, treated 636. Now, for the differences, I just fit an ANOVA, an ANCOVA model using LLM, linear models. So the model is reading score as a function of treatment, the pre-post test indicator, and the interaction between treatment and post-test. So run this model and get the treatment effect here. The treatment effect is the interaction. That's why it's called differences in differences. It's a difference in gains between pre and post, between treated and control groups, right? So the estimate is 0.2855, and it's not statistically significant. Now, this can also be done with a fixed effects model. So the fixed effects model removes the time invariant part of the variability. The simplest one is just first difference. So we'll replace the outcome by the gain between pre and post. So here I'm creating a new data set that's in wide format that have pre and post as separate variables. And then I'm creating a gain. So I create data set here that I will do summary data dd wide and run this. Now I have post, pre, and the gain. So here, running to run the difference in difference as a fixed effects model, I would just do a even simpler linear model with the gain as a function of treated. So this is basically a one-way ANOVA. And run these. Notice that I get exactly the same estimate that I got for the interaction term in the ANCOVA model I ran before. It's not statistically significant. Okay. So this is a repeated meshes ANOVA, essentially, while the other model, the previous one, was an ANCOVA. Now, the standard errors of these are not are known to have less power than the ANCOVA. So ANCOVA is preferable than this approach with the gains for differences in differences. Now, if you have multiple measurement occasions, the classical difference in differences approach is not viable. What we do is fixed effects models. So the difference in differences is a special case of fixed effects models. So here, the research question is, does school mobility between kindergarten and fifth grade affect reading achievement of students? So it's estimating for 5 measurement occasions. The simplest way to do fixed effects is with dummy codes. So child ID is a factor. And I can verify here, class ECLS data child ID factor. And because it's a factor, R will automatically dummy code. So it will create as many dummy code the variables as the number of children minus 1. Okay. And so that will estimate the fixed effects of children. I'll run this. And the problem with this model is that it's so long, sometimes it doesn't converge. This case takes a little bit, but it works. Notice that it's very long because these are all the fixed effects of students. These are the children dummy codes that were actually estimated. So this is essentially a two-way ANOVA where that is one factor is change school with 2 levels, the other factor child ID with as many levels as there are children, right? So it's very long, but you do get the effect of change school here, which is, now it's statistically significant, it is 57.6727. Okay, so here that is an increasing achievement related to changing schools. Now, another approach to fixed effects is by centering. So you individual center the outcome and the predictors. By individual center, I mean take the outcome and subtract the mean for that individual, right? The outcome, so each individual here has 5 outcomes because there are 5 measured ways. Right? You take each of these 5 and subtract the mean for that individual. And you do the same thing for the covariates. So here I'm doing that through code instead of using a package. I'm getting the individual means by aggregating. So I'm getting the means of change school, which is the treatment, the mean, which is essentially the proportion of times that the child moved, the reading score and the math score, which we're not using the math score here. So I'm obtaining the means, then I'm merging the means into the original data set, and then I'm centering. I'm taking here in each of these codes, I'm taking the original variable and subtracting the mean. So change school minus mean change school, reading score minus mean reading score. So the fixed effect is a regression model on the change scores. So we have the reading change score change, which is the gain, as a function of the change in change score. So it's a centered change score. Run these. Now the estimate is correct. It is the same as before, 57.67. However, the standard errors are not correct because observations are clustered with individuals, so they're correlated, and that violation of independence leads to underestimated standard errors. It could be dealt with in multiple ways. Here, first way I'm showing is with the survey package, where I say that the cluster ID is child ID, and then I set up bootstrapping. So I set a survey design where I have bootstrapping, this cluster bootstrapping, and then I fit the model. It's the same model, but now I'm declaring child ID as a cluster. So if I run this, it takes a little bit because it's bootstrapping, and I get the same estimate of the treatment effect, just different standard error. Now, let's say if I'm concerned about some time varying covariates that could be confounders. I could use inverse probability of treatment weighting to control for confounding those to these inverse due to these confounders. And I can use the inverse probability treatment weights here would be for a longitudinal study, right? So the weights are a function of treatment history and previous outcomes as well. Now, in this example, I have already weights calculated for mobility in a variable called EPTW in the data set. I can show you if I do head or names, ECLS data, I have the EPTW here, which was previously calculated. So I can use one way to use these weights is just modify the code for the survey package to declare that inverse probability treatment weight and run the same model. So now I have an estimate that's adjusted with the inverse probability treatment weights, and it's about 10 points lower than the estimate without the weights. Now I can use other ways to do this. Now, if I want to add interactions with time, I would add time as a factor. The advantage of using time as a factor instead of using time as a continuous variable, because time as a continuous variable, if you just add time in this model, you're assuming that time is linearly related to the outcome. In other words, growth in the reading score is following a linear trajectory. But now if you add time as a factor, you allowing each time period to have an individual gain that's completely unrelated to the gain from other time periods. So it's a model with a series of splides, right? Each gain by each time period is separate from the other time periods. So it's makes less assumptions. It doesn't make any assumption about the shape of the growth trajectory. So I'll feed this model with the reading score centered, change school centered, and then I have the time periods here, which are factors. And I will run these. You see, I get pretty different estimates here. I get the change school is, oh, I forgot to have to first transform it to a factor. And then run the model. Sorry, I still didn't work because I didn't copy the whole thing. Okay. Now here. So with time as a factor, you see every time period gets its own effect. Now things changed a lot with this model. Now the main effect of change school is negative, but there is an interaction with time period. For spring of kindergarten, it basically nullifies the main effect. So in other words, there is no change, and then there is an increase, small increase afterwards for each time period. Now, you can use a package to facilitate the estimation of fixed effects, package that will do deviations from the mean for you, like it will mean center for you. One of such packages, PLM, that does panel data. So here we have PLM reading score as a function of change school. It assumes that, makes assumptions about the data, such as it's in long format, and there is an ID variable. Now so I'll run this PLM package, you get my estimates, and you can see that's exactly the same estimate I got with LM, but a different standard error. So PLM does its own adjustment for clustering. Now you can also use a multilevel modeling package for using a hybrid model, because fixed effects can be controlled by group mean centering in a multilevel model. So here we call it a hybrid model, which is it's a random effects model, but it has a centered predictor. The difference here is that you only center the treatment, you don't center the outcome, but you also add the mean, the group mean of the treatment. So this is the percentage of times the individual changed to the model. And this one by child ID means I want random effects of random intercepts. What is the intercept? Random intercepts for each child ID. Okay, so running this, and I'm using LM4 and LMR test because LMR test provides p-values to LM4. So I'm running this, and I get the same estimate I got before, which is 57. So it's the within effect, within individual effect of change. But also I have an effect of the proportion of times changing scope. So this shows that for an individual, there is an effect of positive effect of moving once, but the proportion of changes has a negative effect. In other words, individuals that are changing multiple times tend to have a negative effect on achievement. Now centering is actually not strictly necessary if you add the mean of the treatment as a covariate, because once you control for the mean, the predictor becomes the same as centered, right? So here, the only difference is that I didn't center change the school, but I added the mean. And you can see here that I get exactly the same results for the effect. Now, the effect of the mean here is different, because it's a different composition. So it's while the previous one had separated the with the effect and the between effect. This one has also a combined effect here. So if you want just the compositional effect, like a separate effect of changing school, you would want to do group B centering. So Leite and Algina have a book chapter on centering. Craig Anders also has a book, has a chapter on centering that explain, the differences between these models, where the differences in interpretations for centering and recommendations for centering. Now, you can also include interactions with time in the hybrid model. That's what I'm doing here. So I'm adding the time period and interactions, just like I did in the fixed effects model. And with interactions, a little bit different here because you have different assumptions. To change the scope becomes -13, but then you have several positive effects here of interactions. Now, I can run this hybrid model with the PLM package too, the interactions. And so I have -13 and also a bunch of positive interactions. So the previous, in this one here, I ran it as a hybrid model in PLM, so I ran it as a type equals random, but I can also run as fixed, which is model equals within. So here I run, and here it is. A little bit different effect. This one is non-negative like the other. This one actually looks quite a bit different. Then when I can run with PLM as random but removing the mean, this is a true random effect model. Like it doesn't control for, because I didn't add the mean, so it doesn't control for time, yeah, invariant covariance. And then I can use the Hausman test, page test, to compare model 5 with model 4. And it's not statistically significant, so it shows that there's no difference. There is no correlation between the residual and the predictors. Therefore, you would prefer the random effects model. However, this Hausman test, it has low power to detect differences. So if you have reasons to believe there is confounder, it's better to use the fixed effects model.